Imagine you have a huge pile of Lego bricks scattered on the floor, and you want them sorted by size. If you try to pick the smallest brick each time like selection sort, you will waste a lot of time walking back and forth. Merge sort works like first splitting the floor into two halves, then each half into two smaller halves, and so on until each tiny area has only a few bricks. Then you start merging the tiny sorted piles back together, always picking the smallest brick from the front of each pile. This divide then combine idea is necessary when the data set is large, because it turns a difficult problem like sorting many items at once into many easy problems like sorting tiny groups, and then builds the solution step by step. The key intuition is that merging two already sorted lists can be done in linear time, so the whole process stays fast. The recursive version of merge sort follows exactly the divide and conquer steps described above. If the array has 0 or 1 element, it is already sorted. Otherwise, split the array into a left half and a right half, recursively sort each half, and merge the two sorted halves into one sorted array. The pseudocode is: merge sort a low-high, sort subarray a low to high. If low is greater than or equal to high, 0 or 1 element. Return mid equals the floor of low plus high divided by 2. Merge sort a low mid, sort left part. Merge sort a mid plus 1 high, sort right part. Merge a low mid high, combine the two sorted parts. The merge procedure walks together through the two halves with two pointers, repeatedly copying the smaller pointed to element into a temporary buffer, and finally copies the buffer back into a low to high. This algorithm is completely described by the 3 lines inside the if block and the 2 recursive calls. Explanation: to prove that merge sort always gives a correctly sorted array, we use a divide-conquer invariant. After each call to merge sort a low-high finishes, the sub-array a sub-low to high is sorted in non-decreasing order. Base case: when low greater than or equal to high, the sub-array has at most 1 element, which is trivially sorted, the invariant holds. Inductive step: assume the invariant holds for the 2 recursive calls on the left and right halves, induction hypothesis. After they return, by hypothesis, the left half a sub-low to mid and the right half a sub-mid plus 1 to high are each sorted. The merge procedure then merges 2 sorted lists by always taking the smaller front element, because it never reorders elements inside each half and always places the smallest remaining element next. The resulting combined array a sub-low to high is also sorted. Thus the invariant holds after the merge, completing the induction. Since the top-level call covers the whole array, the entire array ends up sorted. The running time t of n of merge sort on an input of size n satisfies the recurrence. T of n equals 2 times t of n over 2 plus theta of n for n greater than 1. T of 1 equals theta of 1. The term 2 times t of n over 2 accounts for the 2 recursive calls on halves of size n over 2. The theta of n term is the cost of merging the 2 sorted halves, which scans each element exactly once. To solve the recurrence, we apply the master theorem. Here a equals 2, b equals 2, and f of n equals theta of n. Compute n to the power log base b of a equals n to the power log base 2 of 2 equals n to the first power equals n. Since f of n equals theta of n to the log base b of a times log to the k of n with k equals 0, we are in case 2 of the master theorem, giving t of n equals theta of n times log n. Thus merge sort grows proportionally to n times log n, which is optimal for comparison-based sorting. If we write the expansion more concretely, t of n equals 2 times open bracket 2 times t of n over 4 plus theta of n over 2 close bracket plus theta of n equals 4 times t of n over 4 plus 2 times theta of n over 2 plus theta of n equals 2 to the k times t of n over 2 to the k plus k times theta of n. When n over 2 to the k equals 1, that is k equals log base 2 of n, we obtain t of n equals theta of n times log n. Merge sort needs extra memory for the temporary buffer used during merging. The straightforward top-down implementation uses big O of n auxiliary space because each merge call creates a buffer of size equal to the sub-array being merged. In place variants try to avoid that extra array. One classic method is to merge by swapping elements directly inside the original array, using clever rotations or binary search to find the correct position of each element. These approaches reduce extra space to big O of 1, but increase the constant factor of the running time, and make the algorithm much more complicated. In practice, most libraries keep the big O of n buffer because it is simple, fast, and the memory overhead is modest compared to the big O of n times log n time benefit. A sorting algorithm is stable if it never changes the relative order of equal elements. Imagine a list of playing cards where each card has a number the sort key and a suit extra information. If two cards have the same number a stable sort, we'll keep them in the same order they appeared originally, so all hearts stay before all spades if that was the original order. Merge sort is naturally stable during the merge step. When the two front elements are equal, the algorithm copies the element from the left half first. This rule preserves the original left to right order of equal keys. Stability matters in real applications such as sorting records first by last name, and then by first name. A stable sort lets you do the second sort without destroying the ordering from the first sort. Because stability is guaranteed without extra work, merge sort is often chosen when the data carries secondary information that must not be shuffled. Real-world implementations of merge sort add a few tricks to run even faster. Insertion sort for tiny subarrays, for subarrays of size less than or equal to 32, or another small constant. Insertion sort is faster than recursive calls because the overhead of recursion and merging outweighs its big O of n squared cost on such small inputs. The algorithm first runs the usual recursive splitting until the size threshold is reached, then sorts each tiny piece with insertion sort, and finally merges. Bottom-up iterative merging. Instead of recursion, we can start with subarrays of size 1, already sorted, and iteratively merge adjacent pairs to create sorted runs of size 2, then size 4, and so on. This removes the recursion stack and often improves cache performance because the merges happen in a predictable order. Copy-back optimization. During merging, we can alternate between two buffers, source and destination, at each level, avoiding the need to copy the merged result back into the original array after every merge. Tuning the merge routine. Using pointer arithmetic, unrolling loops, and avoiding bounds checks can make the merge step run closer to the hardware's memory bandwidth. These optimizations keep the asymptotic theta of n log n bound, but make the constant factors much smaller, which is why modern libraries, for example C++ std stable sort, use a hybrid approach based on merge sort. When we compare merge sort with quick sort and heap sort, we look at three main dimensions: time, memory, and practical behavior. Time, all three have worst-case theta of n log n time, but quicksort's average time is also theta of n log n with a much smaller constant factor because it works in place and does fewer moves. Merge sort's constant is larger due to the extra copying during merging. Heap sort also runs in theta of n log n, but tends to be slower in practice because of poor cache locality. Memory, quicksort, and heap sort are in place, needing big O of 1 extra space. Quicksort's recursion stack uses big O of log n on average. Merge sort normally requires big O of n auxiliary space. In-place variants exist but are rarely used due to complexity. Stability, merge sort is stable by default. Quicksort and heap sort are not stable unless we add extra bookkeeping. Worst-case behavior. Quicksort can degrade to theta of n squared if a bad pivot is chosen, for example already sorted input. Randomized or median of 3 pivot strategies fix this in practice. Merge sort always stays at theta of n log n regardless of input order, making it a safe choice for data that might be adversarial. Practical choice. For large data sets that fit in memory and where stability matters, for example sorting database rows, merge sort or a stable variant is preferred. For in-memory sorting where extra space is scarce and average speed matters, quicksort is often the default. Heap sort is chosen when we need guaranteed big O of 1 extra space and a simple implementation, but its slower cache performance makes it less common in high-performance libraries.